Hi. Today is April 22. It's the final lecture of this course this semester. Um, a couple of announcements before I start talking about actual math. So remember, the big thing on our not so distant horizon is the um, final exam. It's going to happen on Saturday at 1 p.m. And I'll have instructions for you on how that's going to work. This one, I believe, will be a solo exam. Okay, you'll have 2 hours to work on it, and it will be cumulative. So I strongly encourage you to get started working towards trying to study the material and that sort of thing. My plan is to give you a practice final on Friday, I think, and maybe release solutions later that day. Okay. And I know that probably for many of you, this latest material, I mean, if history is anything to go by, this latest material that we've been learning is the most difficult. That's just the nature of this course. Taylor series and power series and such, that's the sort of most difficult stuff, yeah? And so what I want to do is, take that worksheet, the worksheet that's on this topic of Taylor series. I want to take that worksheet and work through it with you in a video. Does that make sense? So we'll do that, and I'll put a video on YouTube doing that, maybe on Friday as well. So I've got a lot of work between now and then still. Let's see, is there anything? Oh yeah, homework is due today. So make sure you turn that in. Homework consists of worksheets, I believe, 24, 25, 26, and 27. So it's 4 worksheets total. Some of the worksheets are shorter than others, but I would like you to try to work through those. If you have any questions about them, please feel free to ask during office hours. I'm going to open up Zoom office hours as usual from 9 to 11 a.m. as I've been doing every Tuesday, Wednesday, Thursday, and Friday. By the way, if I'm not in the office hours, that if I've gone off camera or something like that, just wait a little while because I'm usually back within 5 minutes. I'm not going to be gone. And if I am going to be gone for a while, I'll let you know and not leave you hanging, okay? Yeah. Let's see. Okay, so I think that's everything I need to say. Oh, one other thing. Sorry. I want to get some feedback about how this semester has gone. This semester has been so strange, so weird, and I don't feel like I have the same level of feedback just on a day-to-day basis from you all. Like I can just walk in a room and look out in the audience and just sort of get a sense for kind of a lot of different things. But now that we have this asynchronous thing going where I'm putting videos on YouTube, it's hard for me to totally understand and know whether or not you're totally getting it. I mean, I'm seeing the midterm scores and they look great. I'm seeing the slips come in, those are great. But I don't know what your sense about the class is, whether you're feeling like you're getting anything out of it or not. So I'm going to send out a survey today that I really, really want you to respond to, okay? And I really, really want you to respond to it. It's the one thing that I really want you to do. It is purely for me and my understanding of what happened in this class. But I really hope that you'll take maybe 5 minutes, maybe 10 minutes, maybe even a little bit longer to be thoughtful, but also to be super sincere and genuine in what you write down on that thing. I know that the danger of that, doing it via email, is that it's not anonymous like the regular student evaluations are. And by the way, there won't be regular student evaluations because of the craziness. So all I can do is assure you that even if you write the meanest thing in this evaluation that I'm going to send out today, even if you write just terribly cruel things about me, I will not hold it against you in terms of your grade or anything like that. That's just not in my programming. In fact, I find the idea of doing that absolutely disgusting. Okay, and I hope that you believe me when I say that, because I'm totally sincere. It is in fact the criticisms, the things that let me know what I'm doing badly, that are the most valuable kind of feedback from me. Okay, so like I said, please just do this for me, please. Okay, 5 minutes, 10 minutes, just do this for me. Give me a response to this survey. I'm going to send that out in a separate email blast, or a separate email that you can reply to. I'll do that after this lecture. But please respond to that, okay? It's very important to me to know how this thing went, because I have, like I said, I'm very much in the dark even still. We are deep into this online thing, and jeez. And I'm not alone, by the way. You know, I've been talking to the other instructors. They have no idea either of what's going on. So you can help them out a lot and make your own experience better in the process. So it seems valuable. Okay, so let's talk about Taylor series. Let's finish up our discussion to the extent that that's possible. I mean, I just want to introduce some new ideas. Before we do that, let's do the post-lecture slip that I assigned you yesterday. I do have a couple comments about them. So yesterday we started our discussion of Taylor series. Here's all the stuff with the oh, this was not first page. Here's the stuff about the calculus of Taylor series, which is really not complicated at all. If you want to take the derivative of a power series, see d dx, here's a power series, we're going to d dx it, you just do it term by term. Okay? And similarly, integrals are done term by term. So in our quest to understand this new representation of functions as power series, one might ask, how do you do calculus with these power series, right? What is it? You know that calculus is a thing that you can do with regular old functions. So how do you do calculus now with this new representation of function as a power series? Well, it's as simple as you could possibly believe. You just take the sum and you swap the position of the sum and the derivative. You see, here they're taking the derivative of the sum, here I'm taking the sum of the derivatives. That's exactly like the sum rule that you had in Calc 1. And similarly, we have a sum rule kind of for infinite sums for integrals. All right. Then we talked about formulas. So, then we talked about how if you're given a function, you can ask the question, well, what is a power series which might represent some familiar function that you're given? Well, we talked at length about how to, the key question is, what are these coefficients a sub n, right? That's the key question, what are the coefficients? And then we did some really fancy stuff in a very kind of nice process to determine that, in fact, if you want the nth coefficient of f, of the Taylor series of f centered at C, what you do is you take the nth derivative of f, evaluate it at C, okay, and you divide by n factorial. It's just a beautiful result. We did that. And then the question that I asked you at the end was, can we find a Taylor series for e to the negative 3x? And I want to give you two methods today for finding that. The first method for finding it is probably the sort of more straightforward route, which is just to use this result here. So the question is, what is the nth derivative of this function e to the negative 3x? So the zeroth derivative, I mean, I can write that, the zeroth derivative, when n is 0. When n is 0, well, what that means is that we don't do anything to the function, right? So this is just itself. This is just e to the negative 3x. That's no problem, right? What's f prime? The first derivative of x. Well, by the chain rule, what we do is we take a negative 3, we put it out front, we get this, right? What's the second derivative? Again, chain rule. This negative 3 comes out and it multiplies by that negative 3, we get this. I hope you are all in agreement. And just for good measure, let's write down the third derivative, so we get this. Now we can ask, what is the general pattern here? And I think, if you're paying attention, what you're seeing is factors of negative 3 piling up here in front of e to the negative 3x, right? And for the nth derivative, how many factors of negative 3 are we going to see? We're going to see n of them. So this is going to be negative 3 to the nth power times e to the negative 3x. Now, a lot of you wrote what I just wrote down. Okay, look at that. And I want to severely advise you not to write things down like this, because, well, this is just straight up incorrect. The reason that it's incorrect is because, remember your order of operations? The order of operations says that exponents happen prior to any multiplication, right? So this n touches the 3, and then we're multiplying the result by -1. So in other words, as written, what this is negative parentheses 3 to the nth power close parentheses. But that's not what we want, is it? What we want is parentheses -3 close parentheses to the n. So if we want the multiplication by -1 to happen before the exponentiation, then we have to use parentheses. So in fact, what we want is this. This is correct. What I had written before was straight up wrong. Okay. So that's what the nth derivative of f is. Now what this advises is that we plug in c. We want to center at 0, so c is 0 here. So the nth derivative of f at 0 is -3 to the n. Some people decided for some weird reason to plug in 0 on the n. That's incorrect. You want to plug in 0 on the x. And if you do that, e to the 0th, of course, is 1. So we just are left with this number, -3 to the nth power. Make sense? And so then what we learn is that a sub n, this nth coefficient, is this quantity, -3 to the nth power divided by n factorial. All right, which implies that e to the -3x should be given by the sum from n equals 0 to infinity. And now we're going to take a sub n and multiply it by x minus c to the nth power. But c here is 0, so that's just the same thing as x to the nth power. All right, so there it is. That's the answer. Now, yesterday we developed this formula for the nth derivative, for e to the x, the Taylor series for e to the x centered at 0. Right, and we came up with this formula here. What I want you to notice, and this is the second method that I want to say for solving the slip problem, is that you could have taken this. So how are e to the -3x and e to the x related? How are these two functions related? Obviously, they're quite related. Well, the way you should think about it is that to get e to the -3x, you replace the x by -3x. Let me say that again. To get e to the -3x from e to the x, you replace the x in e to the x by -3x. Hopefully that makes sense. So if you want the power series, what you can do is replace that x there by -3x, and that will give you the power series. Does that make sense? Now, such methods won't work for something crazy like the e to the square root of x or something like that, right? That wouldn't work. It works when what you're replacing x by is some nice like polynomial expression. That will work out. But if you replace it by something that's not a polynomial, or even worse, like e to the sine x, although why would you ever want to think about this? But maybe, if you wanted to do that, it wouldn't be right just to replace x here by sine of x to get a power series, that is, right? If you were to replace x here by sine of x, sure, you would get something that, a series which converged to e to the sine x, but it wouldn't be a power series. Hopefully you understand what I'm saying. Okay, so that's the second method, is instead of taking all the derivatives, you could have just replaced x here and x there by -3x, and you would have gotten a legit answer, and it would have been exactly the same as this one. Okay, so you might think about that, and we'll talk about more about that kind of thing today. All right, so I want to keep talking about this stuff, and I want to think now about cosine of x. So Taylor series continued. Let's do cosine of x today, because it's good to see this stuff again. So remember, Taylor series, the idea here is that if we're going to have f of x be equal to the sum from n equals 0 to infinity of a sub n times x minus c to the n, if this is true, then this necessarily implies that the nth coefficient is equal to what? The nth derivative of f evaluated at c divided by n factorial. Okay. Now, again, I don't know why I care. It's the math nerd in me. It's the mathematician in me. But when can we make the assumption that f of x is equal to this kind of Taylor series representation? When is it equal to its Taylor series? The answer is not always. And that's what's really fun. That's what really gets mathematicians and things off, is that there are times, there are reasonable functions with infinitely many derivatives and things like that, where these coefficients here are perfectly well defined, but for which f of x is not equal to this Taylor series so assembled, okay? I don't know why I care, but I'm saying it out loud, finding myself say it out loud. But like all the nice functions that we've learned about, all the nice ones, okay, with all of their derivatives and things like cosine, sine, e to the x, all that stuff, they are equal to their Taylor series so constructed. Okay, I'm going to leave that alone now. Oh, and such functions, they're given a name, which are functions which are equal to their Taylor series are called analytic functions. Okay. So what I'm trying to say is that most of the things that you've been learning about are analytic functions, but there are non-analytic functions out there, which you can easily assemble. But we won't go into any of that. If you want to learn about that, take real analysis. All right, Taylor series. So let's talk about cosine of x. Okay, so for cosine of x, let's find the Taylor series centered at 0. Also known as the Maclaurin series, okay? So to do this, what we're going to use, of course, is this great information right here, that a sub n is equal to the nth derivative of f. So let's think about what the derivatives of cosine of x are. Perhaps you know that there's sort of a cyclic or periodic quality to the derivatives of cosine of x. Let's see what I mean by that. So here I'm going to make a table. I'm going to write one column being n. Here I'm going to have a column for the nth derivative of cosine of x. How should I write that? I guess I'll just do this. dn dxn of cosine of x. Okay. And actually, what I want to do actually is, instead of using the letter n, I'm going to use the letter k. Because I want k to go from 0 out to n. So I'm calculating the 0th derivative, the first derivative, the k equal to second derivative, k equal to 3 derivative, and then the k equal to n derivative to find the general pattern, right? And then here we'll evaluate at 0, this quantity. We'll evaluate this at x equal to 0, okay? So let's build a table of values here. This will be, let's do 0, 1, 2, 3, 4, 5, 6, 7, shall we? I don't know. Maybe this is too much. We'll see. So let's see. What's the 0th derivative of cosine of x? It is just itself. And what is cosine of x evaluated at 0? Cosine of 0 is 1. Okay. How about the first derivative of cosine of x? I think from Calc 1 we learned that that's negative sine of x. And what's the negative sine of x at 0? It's 0. What's the second derivative? Well, that's negative cosine of x. Evaluate that at 0 and you get negative 1. Third derivative. Well, what's the derivative of negative cosine of x? I think that's positive sine of x, right? There's two negatives that kill each other. And evaluate that at 0, you get 0. And what's the derivative of sine of x? Well, that's cosine of x. In other words, we see that we get back to here. And because all we're doing is taking successive derivatives, we're going to see that this sort of cycle, therefore, repeats. So the fifth derivative, I don't even have to think. I can just look and copy what I have here. Is that clear? And the sixth derivative I know, and the seventh derivative I know is sine of x. And similarly, these numbers are also going to be cyclic with period 4. 1, 0, negative 1, 0, etc. Okay? So now what we have are these numbers, which go up here in the numerator of a sub n. And the denominator is easy. That's just n factorial, right? But the question, I suppose, is, how can we write this down in a nice way? Because what we see is what we see is, sure, every even term here, every even value of k, we're going to see something non-zero. And what we see is for the even indices, we see the value of this numerator here flipping between -1 and 1. +1, -1, +1, -1. And then for every odd term, we see zeros. Okay? So what we know is that every odd term in the Taylor series for cosine of x, every odd term is going to have a coefficient of 0, right? So we might as well just not even write those. Okay, so we're not even going to write the odd terms down, basically. We're only going to care about the even terms. Now the even terms, again, they flip between -1 and -1, right? When k is 0, we get 1. When k is 2, we get -1 for this derivative, which, by the way, is the numerator of this coefficient. So how can we write that down in a compact manner? Well, let me write down what the answer is, and then I want you to stare at it for a long time until you understand it. All right, so here's what it is for cosine of x. It's that a sub n is equal to -1 how do I want to say this? No, I want to say it like this. A sub 2n is what I want to tell you about. Okay, so let me back up. How do we represent even numbers? Okay, how do we represent even numbers? Even numbers are represented as 2 times some number, right? 2 times something. Those are what even numbers are. So if I want to tell you the non-zero coefficients of the Taylor series here, all right, then the way that I'm going to index those, let me do it this differently. The way that I'm going to index those is by starting an index, let's say at 0, and going to infinity as usual. But then, gosh, this is so hard to talk about. So then, this is going to be 2 times this index, okay, is going to be this k. 2 times this index, n, is going to be this k. All right? And because we are ignoring the odd terms here, we don't need to think about what happens in between. Let's say, like when n is 0, we're going to get k equal to 0. When n is 1, we're going to get k equal to 2. So it seems like we've skipped k equal to 1, right? But in fact, what we're going to do is ignore it because that coefficient is 0. So if we're only thinking about the even terms, we can do that. And then what will this n factorial be? Instead of being n factorial, it's going to be 2 times this index here factorial. Okay? Does this make sense? And then how do we get this alternating sign gadget? It's going to be -1 to the nth power. All right? And then what do we multiply? So this is our coefficient. What is the x term, the x bit? Well, that's going to be x minus c, which is x minus 0, to what power? The 2n power. That's what power. Okay. So now, there it is. We have the cosine of x in our grasp. That was very difficult to understand. But okay, so what I want you to do maybe is instead try to look at this, try to look at that, and compare the two and see that I'm really doing the right thing. It's hard for me to say in words to come up with a good way of saying it that makes it all very clear, okay? Okay. Now, we could do the same game for sine of x, couldn't we? But I don't want to do that. What I would prefer to do instead is to use calculus to think about what's happening here. What do I mean? So let's start with this formula here. So what we know is that cosine of x, this is what we learned just now, is equal to the sum from n equals 0 to infinity of negative 1 to the nth power divided by 2n factorial times x to the 2n power. Yeah? And now what we're going to do is we're going to integrate both sides. So we are just exploring, but what we're going to do is try to learn new facts from previously found facts. So the previously found fact, this one, we're going to try to learn something new from that. We're going to do that by integrating both sides. So let's see what we get. If we integrate both sides, what is an antiderivative cosine of x? Well, of course, that's sine of x. Okay, so if we integrate this side, we get sine of x. If we integrate the other side, well, we get the integral of this power series. But we know that integrating a power series is integrating term by term. So this is the same as the sum from n equals 0 to infinity of the integral of negative 1 to the n over 2n factorial times x to the 2n power, right? Oh, sorry, I forgot a dx here. Right? And if we integrate this term by term, what we get is the sum from n equals 0. And I'm going to put the additive constant of integration. This is typical out front. C plus this. And by the way, there's a plus c out here as well. C plus this sum, what we get is, so if I integrate this is just a dumb constant, right? Doesn't depend on x. This guy here we can just integrate using the power rule. So what we get is negative 1 to the nth power divided by 2n factorial. And then here we're going to increase the exponent, right, by 1. And then we're going to multiply, or divide this thing, rather, by 2n plus 1. Is that clear? Well, what is that? What is the synonym for 2n factorial times 2n plus 1 factorial? I hope you know that that's the same as 2n plus 1 factorial. Okay? And then we're going to multiply this by x to the 2n plus 1. Now, we have this c here, which is an arbitrary additive constant, correct? It can be anything to be an antiderivative here. So if we want to if we want to have a fixed antiderivative cosine of x, namely sine of x, then we should think about trying to figure out what that c is. So I'm saying that sine of x is equal to this expression here for some value of c. And I also claim that we can figure out what c is. Can you think about, for a second, maybe pause the video, and think about how you would figure out what that value of c is? So the way that you can find that c is to just plug in a value for x. So if you plug in x equal to 0, for example, then what we get on the left-hand side is sine of 0, which is 0. And what we get on the right-hand side, please notice that everything dies here on this side, right? If you plug in x equal to 0 here, these numbers 0 to the 2n plus 1, no matter what n is, these numbers will be 0. And so this infinite sum, when you plug in x equal to 0, is just an infinite sum of zeros. So this whole thing here is 0. So yeah, maybe I'll write that. And this whole thing, of course, dies. This is all just 0. So what we learned is that c is equal to 0. And so, you see what we get? We now have a power series for sine of x. We didn't have to do all of this work here again. We just used calculus to figure it out. So this is equal to the sum from n equals 0 to infinity of negative 1 to the nth power over 2n plus 1 factorial times x to the 2n plus 1 power. A new fact. Lovely. It's at this stage where if I had more time, I would tell you about Euler's formula. And I would love to tell you about Euler's formula, which is a statement about the complex exponential e to the ix being equal to cosine x plus I sine x. But I don't have time. Maybe I'll do that at the end of the video where I work through the Taylor series worksheet. I want to go through some. So what we're doing is we're collecting expressions for functions, that Taylor series of functions. Okay. What about another one? How about this one? So here, yeah, let's develop another one. So let's do this. Let me say it like this. Can we find a Taylor series for arctan of x? Now, or of course that's the tangent inverse of x, same thing. Now, I want you to imagine trying to go through these steps that we talked about here to try to find the Taylor series of arctan of x. First of all, what's the first derivative of arctan of x? It's 1 over 1 plus x squared. Now imagine taking the second derivative. You're going to need to either use the chain rule or the quotient rule, right? Then imagine, I mean, it gets really hairy really fast, right? It gets disgusting super fast. Like the third derivative the second derivative is easy, and now third derivative is just kind of a headache. Fourth derivative is even more of a headache. It just gets worse and worse, okay? So I want to avoid doing that because I'm lazy. And maybe I can learn some other facts on the way. So this is going to be our overarching goal. Now, you might not be able to do this, right? I'm just trying to, I'm not trying to say that you should be able to do what I'm about to do. I know what I'm doing because I've done this before, and I know how these things connect together, but you don't yet, and that's fine. But I do want to take you on this little adventure that I know we can all do. So before we do anything else, let's think about this very simple power series for a second. N equal to, 0 to infinity of just x to the n. I believe this is what I want. So this is a power series, right? Centered at 0 with coefficient of 1 over and over again. All right? It's a power series, so it's a function, right? You can check that its interval of convergence is include -1, exclude +1. But everything in between, -1 to 1, including -1, but excluding +1. Did I say that right? No, I'm sorry. What am I talking about? I'm totally crazy. I've lost my mind. No, the interval of convergence is from -1 to 1, excluding both endpoints. Oh, right. And how do I know that, by the way? So sure, I could go through the ratio test stuff. Remember, that's how we find interval of convergence is. I could go through that the ratio test and do all of that. Or I can realize that this series here, okay, is a geometric series. Do you all see that? This is geometric. I don't know if I've ever said this out loud. It's geometric for this guy. And it's geometric with A equal to, what is the first term, right? A is always the first term of a geometric series. It's 1 here. And what's R? It's X here, right? So it's geometric. So as long as the absolute value of X is less than 1, this thing will converge. And in fact, we know what it converges to. So we know that this thing is equal to 1 over 1 minus x. How do I know that? So it's equal to a over 1 minus r. If you look back in your notes on geometric series, I will have told you that if the absolute value of r is less than 1, then not only do we know that this series is convergent, but we know that it converges to a over 1 minus r. So what is a and r in this case? Well, I got them written right there. So this is equal to 1 over 1 minus x. In other words, this function, 1 over 1 minus x, okay, has as its Taylor series, centered at 0, this. All right? Okay, so we have that this guy here is equal to that guy there. And I want to think of it like kind of turned around. So maybe in fact, I'll even write it. Just so it's, I want to keep the function on this side and the Taylor series on this side. So now what I'm going to do is I'm going to replace this negative x. So what I want, and maybe you can think about why I want this. What I want is now this Taylor series. Can I find a Taylor series for 1 over 1 plus x squared? What I'm trying to get at is, can I find such a Taylor series if I know this Taylor series here? Yeah, the answer is yes, I can do that. How? Well, it sort of goes back to what I was saying about that post-lecture slip. Remember, we knew the Taylor series for e to the x. We wanted the Taylor series for e to the negative x, right? Or e to the negative 3x. And so what we did is we just replaced x by negative 3x, right? So we can do something similar here. We can, okay, that's good. We can do something similar here, where we're going to replace this x here by negative x squared. So in going from this line to this line, what we're doing is replacing x by negative x squared, right? If we replace this x by negative x squared, we get this expression. So if we replace x by negative x squared over here, we'll get the Taylor series for this crazy guy here. So we get negative x squared, this whole thing to the nth power. And notice the care that I'm taking because of the order of operations issue. So this is the same thing, of course, as the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n power. Is that clear? And now what are we going to do? So remember, our goal was to figure out the Taylor series for arctan of x. Now what we're going to do is we're going to integrate both sides. Because what do we know? The integral of 1 over 1 plus x squared is arctan of x plus c. And remember, to integrate, you just integrate term by term. So I'm going to do this fast. This is c plus the integral of n equals 0 to infinity of negative 1 to the nth power divided by 2n plus 1 times x to the 2n plus 1 power. Right? So let me continue on a new page. This is page 2, I believe. So here's the work that we had there. And then if we continue, well, I want to know what c is, right? So what I can do is plug in 0. And what we get is that arctan of 0 we know is 0. The tangent of 0 is 0, so the arctan of 0 is 0. And that's equal to what we get by putting 0 on this side. But if we put 0 on this side, because there's no constant term here, these are all, this series here is 0. So this is c plus the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 times 0 to the 2n plus 1. And the point is that this whole thing here dies. Right? And what we're left with is c is 0. So we learn that arctan of x, also known as tangent inverse of x, this is the nomenclature I've been using, the notation I've been using, but which I'll, full disclosure, state that I hate, is equal to 2n plus 1 over x to the 2n plus 1 power. More facts. So from the familiar fact about geometric series, okay, we were able to deduce a fact about the Taylor series of Arctan. Okay. All right. And because I think it's fun and funny, I'm not sure if funny is the right word, I want you to notice something. So this is just a little fun little aside. Plug in x equal to 1 for a sec. Into what? Into this here. So on the left, we get tangent inverse of 1. And on the right, what do we get? We get the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1. Right? And then we have 1 to the 2n plus 1 power. But 1 to any power is just 1. Right? And so I'm not even going to write it. We get this. How interesting. Because what are we saying? So first of all, we know what the tangent inverse of 1 is. That's pi over 4. Okay? And what do we have on the right-hand side? Well, let's just plug in some numbers to figure it out. So when n is 0, let's see. If n is 0, we get negative 1 to the 0, which is 1, over 0 plus 1, which is 1. 1 over 1, which is 1. How about when n is equal to 1? Well, now this sign gadget will be negative 1, and downstairs we'll have 2 times 1, which is 2 plus 1, which is 3. So we'll get minus 1/3. If we plug in n equal to 2, we get 1 upstairs, and we get 5 downstairs. And it keeps going like this. The pattern continues. So what I'm saying is that pi over 4, pi, remember, please, is the ratio of a circle's circumference to its diameter. And what I'm saying is that you can compute that quantity, pi over 4, by, or you think of it this way, you can compute pi by adding up 1 minus 1/3 plus 1/2 plus minus 1/7, etc. You can add up these numbers. Okay? The infinitely many alternating reciprocals of odd integers. You can add up all of those numbers, and what you will get is a series which converges to pi over 4. By the way, we know that if we were given this series, maybe it's not obvious that the series converges or not, but it does. You know why it converges? It converges because of the alternating series test. This is an alternating series whose sequence of terms is going to 0, right? And so this isn't a convergent series, by the way. But not only that, now that we have this relationship between this power series and this function, we know what it converges to now. It converges to pi over 4. Okay? So if you are or one of those mega nerds that is super interested in the digits of pi, like knowing what it is out to trillions and trillions and gazillions of digits and all of that, one thing that you could do, one method that you could use to computing the digits of pi is to calculate this quantity with some obscenely large number of terms, right? Do the partial sum, not from n equals 0 to infinity, but rather from n equals 0 up to like some enormous number, like 1 trillion, trillion, billion, billion, etc., right? And that would give you a lot of the digits of pi to some degree of accuracy. The question is, how quickly, and this is a question not for this class, but rather for something like numerical analysis, which you mechanical engineers will eventually take. Or actually, I'm not totally sure if that's true anymore. I'm confused about the curriculum changes that are in the ME program. But it is the case that this thing converges to pi over 4. It does, but it does so slowly in some sense. That is to say, you need a lot of terms of this series in order to approximate the value of pi over 4 well. So this is not a very efficient way of computing the digits of pi. Okay. But it's a pretty cool fact, right? Pi over 4 is equal to this crazy thing here. It's pretty interesting that that should be the case. One moment, please. Let me just look here to see if there's anything else that I really want to say. So everything that I want to say, I think, about Taylor series will be in this worksheet. And I really would like you to try to do this worksheet, okay? Because, well, it's important, all right? It's important. Maybe, so I've got 5 minutes. Maybe in the time that I have, no, I don't have time. Okay, well, that's enough for today then. What I would like you to try to do is, again, work through the worksheet, and then we'll talk about solving more of these Taylor series problems in the context of working through that worksheet, okay? In the meantime, I would like to talk about, and I'll send this out in an email. This is not the post-lecture slip, okay? I'm going to go ahead and say there is no post-lecture slip this morning, okay? Instead, what I would like you to do is to think about the following thing. So I want to get feedback from you, like I said at the start of this lecture. All right. What I'm going to do is I'm going to send you an email, a separate email from the sort of morning email that I send you every morning. I sent you one this morning, April 22nd. Yeah, no, let me say, no post-lecture slip. I don't know. I'll just say it. Hey, no post-lecture slip today. This will make my life easier because I won't have to respond to about 1 trillion emails. But I like getting those post-lecture slips from you because it's the one form where I know, one thing where I know where you're actually present. A lot of instructors have like no clue who's watching their stuff, and they're just like, they don't know because they don't get that kind of feedback. So it's a very confusing time for us as teachers. So that's the spirit in which I would like to get feedback from you about a couple of things. So one thing that I would like you to do is to rate the following sort of gadgets that we have in place on a scale from, and I'm going to send all of this in email, so I don't expect you to write what I'm writing right now, but I'm just going to say the questions to let you know what it is I sort of want to hear from you. Rate on a scale 1 to 5. 5 is good. 1 is bad. Your feeling about, and I'm really just making this off the top of my head. 1, the transition. So by the transition, I'm referring to those days where it became very clear, or I don't know, it was clear to me anyway, that this coronavirus thing was super serious and we needed to be responsible human beings and not do in-person classes. Okay, I want you to tell me how that transition went. And okay, so if I'm being honest, if I'm being sincere, then to me that transition was kind of bad. Like I could have done it better. I was frazzled. I didn't know what I was doing, and I just sort of vomited out as much as I could all the ideas that I had, or many of the ideas that I had, without thinking about how they would sort of come together, how easy it would be to communicate with you, the transition process. So I would say this is like a 2 or a 3, in my opinion, on a scale from 1 to 5. Your feeling about the Twitch stream. So that that I'm lecturing right now on Twitch. How do you like that? Do you like it? Do you hate it? I think it's fine. It's a pain in the ass for me to get up in the morning, but to me it's okay. So whatever. I would say that's like maybe a 4 or 5. It's fine. 4 maybe just because I have to wake up so early in the morning to do these things. But yeah. How about the YouTube? So by the YouTube I mean me uploading these things. Is that good for you? Is it bad for you? I mean, to me, that's just great. I mean, that seems like really good. So I would give that a 5 personally. How about the email stuff? So what do I mean? I mean in particular the so two things maybe. One, I would like you to rate the morning email communications. So to me, this was really important for organizing my own thoughts about the class. So I would give this a 5. And I also want to know how you feel about the post-lecture slips. Did you like them? Did you hate them? Were they burdensome? I know for some of you got a lot out of it, right? Some of you got a lot of, I think, because I was able to communicate with you about a particular problem, when you might not otherwise come and talk to me about it because you're scared of going to office hours or whatever, you got help that you wouldn't otherwise get. So I think these were amazing. I really like these. This was a 5+ for me. But it was a lot of work. Holy shit, it was a lot of work for me because I replied to literally 100 emails come in. 50 emails come in from you guys, but then like if you do something wrong, I'll correct you, and then there's a back and forth, which I really like, but it's a lot of work to stay on top of it all. Yeah. So tell me how you like those post-lecture slips. Tell me how you like the Zoom office hours. I know many of you didn't take advantage of it, but maybe it's just reassuring for you to have them, or maybe you don't like getting on Zoom, whatever. But tell me about those. Okay? And maybe more generally. So this is the feeling about the course. So so this is still on a 1 to 5 scale. I would like you to tell me about the worksheets. In particular, I want you to tell me, how do you feel about the worksheets relative to, like, let's say, regular old book learning, where you have a book with tons of exercises in there available for you to do? I know the worksheets, one of the disadvantages of those things is that there's maybe not enough exercises. That's definitely possible. How do you feel about that? To me, the worksheets were also a pain in the ass to make, but I think I really liked them. I would really like those as a resource for learning. I think they're good, so I would give those a 5 personally. But I don't care what you write. What I wanted, and I'll say this at the end, and maybe your overall view of the course. Okay, how did you feel about it? And in particular, so what I want is written feedback. In particular, I want criticisms. So I'm going to write all of this in an email. I'm just organizing my thoughts now so you can start thinking about them. But let me say, okay, I said this already, didn't I? And I know I'm going over time, so you can cut the stream if you got to go to class or something like that. But I don't care, okay? I do not care if you are mean or cruel or insensitive or whatever to me. I would never, ever let criticisms of that form affect your grade. That is not in my programming. And I don't know how to impress that upon you. So I know that this is not anonymous. But if you think I give a shit about, you dinging me on any one of these things, you're out of your mind, okay? You're just wrong about that. I would never, ever do that. Never, never, ever do that. In fact, I think one of the kindest things that a student can do for his or her instructor, namely me, one of the nicest things that you can do is to give me legit, honest criticism that I can read and evaluate as far as my judgment is concerned. So if you give me a criticism like, you assigned too much homework, well, obviously I'm going to take that criticism. Well, never mind, let me not say that. I will look at that criticism and I will say a silent thank you to you. That thank you will move through the ether and will warm your heart. Okay. What am I talking about? Please, honesty, sincerity. I can't get better, and unless you give me honesty and sincerity. So in this written feedback criticisms thing, it's nice to hear when I'm doing well, but if that's all you write, it doesn't do a whole lot for me. Okay, it really doesn't. I don't get a lot out of that. What I get a lot out of is comments of the forum. Could have done this better. You could have given us more exercises, but you didn't. You could have been less of an asshole about this quality of the class or this aspect of the class. You could have been harder on us, maybe, when it came to this topic or on this part of it. Yeah. I'm going to add more things to this because I just realized there's also the homework component, right, which I didn't include on this stuff. All of these things, what I need is honesty from you, okay? And this is optional. I'm not going to fail you if you don't submit something, but please, 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 okay? Please. It's the one thing that you can do for me. It's like your gift to me, okay? I don't want anything else. This is what I want from you, is I want your sincerity for just a little bit. I really want it. I love you. That's that, okay? And this is the last lecture. We're all done. I'm going to open up office hours now, and I'll send out an email with the Zoom URL, okay? I love you all very much. Goodbye.